this is an introductory tutorial. Our goal is to sort of get all of you up and running with using requests, Beautiful Soup, NumPy, Pandas, Matplotlib on Jupyter Notebooks. But more than that, like, you can scrape data and you have data on your computer and you can do stuff with it. But we also try to go through some of the thought process and developing good questions that you can answer so that you can develop, a really robust data science project that does what it is you need it to do. So we have all these goals here. So let's say, to start off, we are going to pretend that we are movie producers. So what do we want as a movie producer? We want to create a movie that is going to make us piles of cash. And there are you can imagine that there are some things that are more likely to make a movie worth a lot of money than others. It could be maybe if a movie comes out at a certain time of year, it'll be worth more, or people are more likely to see it. Maybe people like to go see movies around the holidays. Maybe if it comes out around the holidays, you'll be more likely to see that. So we want to figure out what these factors are that are going to make us a movie that's going to make a ton of money. So one way that we can start with that is we can start by looking at data from a bunch of other movies and see which of them made a lot of money. Last year, it was Black Panther, was the #1 movie. It was pretty amazing. So to start off with, let's break into small groups. Maybe we will say maybe we can say each row is a group. You can break up however you want. But the goal then is to list out some features that you think you might want to consider as you make your best movie ever. Like, what do you think are going to be the predicting features? And we'll do that for 5 minutes. How did it go? Did everyone come up with some ideas? Are there a couple groups who want to share some? Maybe, do you want to share a couple of your ideas?
This side did some more general ones, like...
we had the value of a brand, general reboots, how much of a platform it has, whether it has the amount of money needed to launch a huge production, what kind of message it's making, and whether it resonates with the culture or not.
Awesome. Those are some great questions. I guess if you're trying to design a data science project around that, what sort of things would you look at? Like, how do you measure a brand?
Yeah, probably an amount of money that it's been making over the last X many years. However many years back you want to go would probably impact your final decision as well.
That makes sense.
With IMDb, you can probably just look at the studio, right?
Yeah.
If it's Marvel, studio, is it going to make more money than 20th Century Fox? Right.
How do you know which one's better?
Well, we're assuming our predictive value is like how much money it makes.
Makes sense. Awesome.
And then we have some more specific ones, like The Rock, superpowers, and explosions.
Believable. Awesome. Anyone on this side of the room? Yeah.
One thing that we discussed to add to all of those in terms of making money, not necessarily just being a good movie, because we had that kind of discussion about how those two things aren't always equivalent. But the number of theaters that it's released in will have an impact on how much money it can make. Sometimes there's great movies that are released in theaters and generates later on.
Yeah, that's a great one. That's actually one that we're going to be looking at here today as well. Awesome. So our next section, we're going to talk about asking good questions. There are so it turns out the questions that people actually want an answer to is like, this, will my movie be a box office hit? That's the answer. That's the question everyone wants an answer to, but there are lots of times to get a question that you can actually answer with data science, you need to reframe the question a little bit. So often what people want is a causal answer. Like, if I cast The Rock, will my movie be a box office hit? things that tend to be a little bit easier to answer directly with data. Causality tends to be difficult to prove. You can say, you can show that things are correlated. Like, if more movies that cast The Rock are a box office hit, or getting likelihoods as well. Like, given that we get this actor, what is the likelihood that the movie will be a box office hit? So it's important to ask these questions in a way that you can actually answer. One of the most common mistakes that I see in data science projects is it's one of the first two. It's either, everyone, if they get something that's correlational, they then try to frame it as causal, or they ask it a questions that's vague, and then they aren't really able to pick through the data to get to exactly what the answer is. So it's great to ask questions like the last two. This is because correlation does not imply causation. This is a great example of that if you look at this. It actually correlates really well. If you look at the two variables of the number of people who drowned by falling into a pool correlates with the number of films that Nicolas Cage appeared in, such that, if I just saw those lines, I'd be like, yeah, those things are related, definitely. But they are not. So to ask the best question you can, like some basic guidelines, are you can use some of your experienced research or educated guess to sort of narrow down your question. Like, if you really think that what makes a movie make a lot of money is something like, the power of the brand, then being able to narrow in on how exactly you're going to measure that brand, and how you're going to then figure out what correlates with the brand as you measured it. And you might even want to think of a couple different measures of the brand if you want to make sure that it's something, if you want to sort of make sure that your measure isn't off as well. So if it's a vague question like the first one, then you might be able to rewrite it in terms of a correlation, like does something like this correlated, is this factor correlated with that factor? And try this, the number 3 is actually a big one. It sounds obvious, but try to make sure that you're only asking one question for each of your variables. And that also it just simplifies things a lot if you can do that. If you absolutely need to argue for causality, there is some research on that, and there are a number of blog posts that summarize that pretty well, which are in the links in here. So we are going to break out again. This time, maybe that seemed a little long, so maybe we'll do this one for 4 minutes. And the goal is, can you take either some of your features, or you can come up with new questions, but phrase them as good questions that you think that we can answer with data. And go ahead. How's it going? Do you want more time, or are you guys done? If you want more time, raise your hand. Okay, awesome. Does someone over here want to tell me one of their questions?
Okay.
Yeah.
So we have a good list. We said which genre of film makes the most money?
Okay.
Is the actor or actress's salary related to ticket sales?
Okay, so I get that first one. So for the salary related to ticket sales, so that would be a correlational. All right, awesome.
How does a film's rating correlate to the box office take?
Okay, another correlational one.
Is there a relation between time of year and the ticket sales?
Awesome. Yeah, that is another great one. So would that be correlational, likelihood?
I would probably say it's more likelihood kind of thing. It's more likely to succeed in some of those versions.
Makes sense. I saw a hand over there.
Yeah, we were wondering if the total number of Oscar wins for the entire crew would be correlated to box office performance, or if the average number of Oscar wins for the whole crew might be correlated to box office performance.
That makes sense. So you're saying like if one, so it's sort of like a measure of star power. So like if you have a really big star, it will do well. Or if you have 10 big stars, it will do even better than one really big star.
And also things like if there's people that were doing the score that won Oscars for that previously, that the movie has a really good soundtrack, then that might.
Oh yeah, that's another good thing is, I guess, how do you measure that last one?
Well, I would think with the same way with number of Oscar wins, because you can win Oscars for movie soundtracks, right? So maybe if people who were working on the soundtrack had previously won Oscars, then, I don't know.
Okay, so once again, it could be also be like,
Or Grammy wins too.
okay, it's like star power of the people working on
Yeah.
the music. That's another great one. So that would be correlational, right? Awesome. Anyone else?
We had, how does like a budget correlate to, does a higher budget correlate to a better?
Oh yeah, that's another great one. Awesome. It sounds like you guys. Oh yeah, that is a great idea. And in the future, I will repeat the questions. Just because I hear you doesn't mean everyone else can hear. Awesome. It seems like you guys are great at this. So the next step is, so at this point, what we've gone through is we've said we've started thinking about what sort of features might be important. And we've started framing some good questions, which is actually a hugely important skill. So I'm really excited to see that all of you are doing so well on it. And now we're going to think about where we can get good data to answer these questions. So I guess what are your thoughts for where you might get data to answer some of these questions? Yes. Yeah, that is a great one. Unfortunately, they have scraping terms of service. You can't just go and scrape everything from IMDb. I wish you could. What IMDb does is it's actually they select a sample of movies that they're okay with the information being public. So it's not all the information. That's why there's such a thing as IMDb Pro. But that is, if IMDb actually made all this data public, I would be so excited.
EMDB?
What is that?
EMDB?
What's that?
The movie database?
Okay.
Another one, but it's open source.
Oh, cool. Yes.
Maybe DBpedia?
What's that?
It's like a machine readable version of Wikipedia.
Cool.
What is it? I couldn't hear it back here.
What was it?
DBpedia.
DBpedia. It's like Wikipedia of the movie information, right?
Well,
Just all information. Awesome. Which actually is another one. Wikipedia is also awesome. So I guess what makes some of these places good places to get data? So this is a whole bunch of things that we listed, some of which we used, and some of which we didn't. But particularly, what makes the nice things that you can get is, or what I would say, what makes a good information source is A, it actually having good information, and then B, how easy is it for you to get that information? So it's nice to find places that have somewhat structured data. So in this, we can, so some examples that we used here were like Wikipedia. Rotten Tomatoes is another good one. The nice thing about all of these things is like if you look at Wikipedia, they actually have a little box where you can get information. This little box in the corner where you can get information like when the movie came out, how much it made, who starred in it, and so that box looks like a little HTML box. So you can get information from each row, and you can sort of there's some amount of predictable information there. And then, I'm sorry, I didn't get your name. Yeah, what was your name? Mario? And then like Mario brought up with IMDb Pi. The other thing to watch out for is the terms of service for what you're scraping. This is what prevented us from just scraping IMDb directly, which would have been lovely. So make sure that you read that. Lots of times you can do it for limited use or for academic use. Awesome. So I'd say that a lot of the big things for this are trying to find structured data and trying to find good data sources that have terms of service appropriate for your use. So our next step is to actually start scraping. So we've gotten some structured data. This is just loading in all the imports that we're going to use. If you have any questions about this, feel free to let us know. And then what happens here is first we use the requests library. Who's familiar with the requests library? Not very many of us. That's amazing. So the way requests works, let's see, I do not have a great visualization here. But the way requests works is what it does is what we're doing here is we run an HTTP GET request. So what it's doing is it's saying, site, go and give me all of your HTML and give it to me and I will just store it here on my computer. So you're actually getting, if you look at a site like, so you can go and look at a site like Wikipedia Black Panther. So there's all this cool information here in this box. We have who's it directed by, who's it produced by, who's it starring, who did the cinematography. And actually, if we right-click and we view page source, the internet's struggling a little bit. But we also have all of this like relatively structured data. We can go in and we can look at, particularly, it looks like this is the table that we care about. So we can go in and we can look at all of that information and we can look at things. Maybe it looks like this is a class of info box. So maybe we could then search through this and look for tables with a class info box. What request does, though, is it gets that HTML and brings it onto our computer so that we can start searching through it. Then, but if you do this too quickly, if you just run a GET request in a for loop, lots of times the server can tell that you're taking information very quickly, and lots of times you'll get throttled, so you won't be able to get the data you want. So this is why we have this time.sleep here. So if you're writing your own scrapers at home, I do recommend using the sleep method. So you're slowing it down so that it plausibly could be a human clicking. So this is saying wait 1 second between each time that you run the requests. And then what this gives you, so you make this request and it gives you back an object. And it has the text, all the text from the web page, so you can start searching through that. And it also gives you a response to say if you got the web page. So to see those, you can look at, so an HTTP response 200 means that everything's okay. If it's not okay, you can look at these list of HTTP codes to see what you got instead. And there are a number of them that there could be. Or my particular favorite is this one. It's HTTP codes as cat photos, which is much more entertaining. So you should get a response 200. And then you should be able to, and then there's also a text message which shows you whether or not you've gotten the appropriate text. Awesome. So then our next step is for all of you to try it out. What you can do is you can, what we're looking at here is Box Office Mojo. So this is what Box Office Mojo looks like. Particularly, I think we want 2019. So this is amazing for data scraping because this is a very nice 90s looking HTML table. And if you look at the view page source, It still looks like a nice 90s HTML table. So that's what you're going to do next, is make an HTTP request to get everything down on your computer, and then start searching through there to get familiar with the HTML. Let's give it 5 minutes, and if you need more time, we can extend it from there, and let me know if you have any questions.
How do you get to the 2019 part? In the link?
Yeah, so that is a great question, and this is actually,
Because the link that is in the thing is
Yeah.
218.
right, so,
But the same thing.
yeah, so actually this is a great point, which I should go over with everyone. Thank you for that question. Okay, so notably, if you want to get different information, there are a couple things you can look at. One is, we talked about the source. The other is looking at the parameters of the URL that you're looking at. So in this case, everything after the question mark is a parameter defined by the site. And so this defines the release date, the view, and the year. So if you want to get different information, you can change that by changing the parameters. So when I'm figuring out what information I wanted to get to write this, what I would do is I just went to the website, said what is in the URL, and there's a good chance you might actually, rather than getting just one page, you might want to get 2 pages. So then if you click to the second page, what does that URL look like? How does it change? Quick show of hands, who's familiar with Python string formatting? So this is like a string with like a %s or a %d in it where you format things. Yeah. Okay. Okay, who's not familiar with it? All right, great. It's always hard to tell because not everyone raises their hand. So it's like a third is familiar. Does that mean not 2/3 are not unfamiliar? Okay, so this is an example. This is the solutions, so that's not important. But anyways, what you can do with a string formatting is you can do, so we saw earlier that the change between the URL is the year changed and the page number changed. In this case, we can do something like this, where we say the page is %s, and then on the outside of the % here, we'll get a page in a year. So we can do this instead maybe with a Python terminal. Escape.
What that's allowing to happen is it allows a substitution to take place.
Yeah, I'm about to demo it. Okay, so if we have this string, message, so I love potatoes. But someone else might love pineapple. And we might want this to say something different depending on different things. So what we can do to make this a little bit more flexible is we can make our message %s, and then have a % here, and say, and then instead put in a variable name. So we'll say, we can make a things I love variable. And this is potatoes, pineapple, with quotes, puppies. And then we can say for I in things I love, message equals I love message equals I love %s percent I, and then print message. So we were able to substitute something different in for the string. And if you're substituting two things, you can instead do that with a parens after this. So it would be message I, comma, j. And then we do that by having another %s, like this, %s. So that is how the string formatting works. Yes?
Is that better than like just concatenating?
You could just concatenate it. That's another way of doing it. But the nice thing about this is it lets you substitute things in. So you can do more complicated things with this string formatting. So at this point, what we're doing is we're getting all of this text down onto our computer, and then we're going to use Beautiful Soup to make it searchable. So all you need is data. You don't need pages of data. If you have any data, we can move on. All right, awesome. Okay, so now we will talk about Beautiful Soup. Or are you guys ready? Think a lot. Okay. We good now? All right, awesome. So next we're going to talk about Beautiful Soup. So what we just did is we took the text that was up on the server hosting the web page, and now it's down on our computer, and we can search it, and we can do what we want with it. And one way, and how can we search it? Like one way we could do this is we might use something like regular expressions, but that is going to be super annoying. So we're not going to do that. Instead, we're going to use this awesome library called Beautiful Soup. And what Beautiful Soup does is it makes everything, it sort of takes your HTML and it turns it into a tree format. So an example, if I'll zoom in, of this simple, a very simple example here is something like this, where we have an HTML which has a body and a header tag. The header tag contains one heading, H1, and the body tag contains a paragraph. And what this turns this into is like you have a parent node of HTML, which is the largest thing, and then it has two children, head and body, which have children, H1 and paragraph. So now what you can do is you can click into the Beautiful Soup documentation, where they tell you about some of the things that you can use. Like you can find all titles. You can look at particularly what the header is of the title. So you can look at some of these functions that are used to sort of then search through the tree like this. And then you can explore your text data to pull out the data that you need from this Box Office Mojo table. And if you need any more hints, check out this example. I will just want to point this out to you. So this is right under the Beautiful Soup section. Try it out. This example is sort of step one in getting started. That is a lot of messy text, but this is sort of step at the end of all this. Not the most beautiful display. This section, the Using Beautiful Soup section, at the end of that link. So if you click in and scroll to the bottom, it will help you pull out the table, and then you can pull out everything else from there. So the goal of this is to make your text queryable and find something in it. Particularly if you pull out all the titles. That's a great start, if you pull out all the titles of the movies. Awesome. So in my quick walk around the room, it looks like a lot of you are off to an amazing start. Either most of you have managed to at least get a title out with Beautiful Soup, which is awesome. To finish things up, what you would do is you would put more titles into a dictionary, and then you can put that dictionary into a pandas data frame. And there's a really easy pandas dict2 data frame function that you can use in order to create that data frame. So our next step, so at this point what we've done is you've made a request to the server, you've gotten the text down onto your computer, you've made it searchable so that you can search through it and get text and the information you want out of it. At this point you could get information like the budget, what year it was developed, and you can start answering some of those questions that you were thinking of. And so now what we're going to do is we're going to load it into a pandas data frame, which for those of you who have used R, pandas data frame is very similar to an R data frame. And then here we say that each row is a movie and each column is a feature of that movie. So, and whether or not you've managed to create a dictionary, you can move on to this step. Because we have a data frame that is pickled and waiting for you. So we read in this data frame, and then we can check out the shape. And if you have not used, I guess, how many of you have used pandas data frames before? Awesome. That's the most of anything so far, so that's great. So anyways, if you look at the data frame.shape, it tells you what shape it's in. This is always a great first step, just to make sure that your dimensions are right, and there are 800. So in this case, we're saying that there are probably each row is a movie, so we're looking at 815 movies and 25 different features. And the things that we're looking at here are we're looking at the movie budget, information about the cast, who the director was, how much it grossed, what the rating was, how much it grossed in its opening weekend, what the opening theaters were, and so on and so forth. So we have a whole bunch of information in this data frame. And then to see exactly what information we have in the data frame, we can use the dataframe.keys method to look at what we have, and we have all the titles here. So we can actually start to think about some of the questions that a lot of you asked. We have information here like what studio did it come out of? So if we know which studios are good, we can see if the studio is helpful. We have information about when it came out. We have information about the rating. So there's a lot of stuff that we're doing here. So there are a lot of features that we can explore, some of which you guys mentioned and some of which we didn't, such as, is the movie budget helpful? Is the amount of money that you earn in the opening weekend predictive of how much money you make in the long term? Are having a certain brand behind you better? So to start off with, before we draw any conclusions about our data, we want to start by just looking at our data and seeing how it relates to one another. So what we're doing is we're just going to make a whole bunch of scatter plots to get a correlation and run a linear regression. So we did this for one item here. So this is, we're using Seaborn here, the Seaborn reg plot. And so we can pick the Y is gross. So gross is one of the titles here, one of our keys, opening gross. We use this data frame. And we get, I'll actually make this a little bit smaller so you can see it. So what do you think? Is gross revenue correlated to opening weekend revenue? Do you think? Yeah. So it looks like it's pretty correlated. So it looks like if you have a really good opening weekend, there's a good chance that your movie is going to continue to make money after that opening weekend. So it seems like, so do we think that these, do we know that these things are causational? No. But it seems like the data fits. It seems like there's at least a good correlation there. And really, maybe that's all that we need to make our movie that is going to make us that big stack of money, is if we get enough good correlations, maybe that's going to be great. We do this with a few more. And so you can use the same pattern that we used here to plot, then also, it looks like this is the same one. So you can do that same plot. And then you can also do the gross revenue versus the allocated budget, gross revenue versus IMDb rating, and see what you think of each one of those. And we will do that. We'll give you 5 minutes. And if you have any questions, please let me know. So the goal here is just you have a pandas data frame. You explore a little bit of how to use that pandas data frame, what some of the main functions are, and then make a plot to look at that data using that pandas data frame. And if you finish early, you can start working on the bonus, which is you can start exploring some of the other features that you thought of. How's it going? Who has managed to make at least one plot? Awesome. Who has managed to make those 3 plots? Awesome. Okay. So what have you learned? Yeah, that's a good one. What did you learn from the first plot? So the first one we're looking at, so we looked at this one and we discussed this a little bit. This looks like gross revenue is correlated with the opening weekend revenue. This title is just off. So then this one, it looks at the number of opening theaters versus gross revenue. So this answers, someone over there had come up with this idea of maybe there's an optimal number of theaters that you can put the movie out in. And it seems like there actually is an inflection point here sometime around like between 3,000 and 4,000, where you're likely to make more money if you put it in a certain number of theaters. And what do you think of these things over here? Yeah, so no data. It's possible. For some reason, there were no opening theaters. Like maybe this was like a Netflix movie or something like that. Or maybe people just didn't put all of the right information in there. It's great when you're doing this to look at this data. Another question, a reasonable thing to ask is, what the heck is this movie? Like, what's going on there? Yeah, probably. Yeah. So it's nice to crazy check your data here. What do you think of this? Yeah. It's maybe a little bit correlated, which I guess kind of makes sense. It's like, if you have a big budget, you might also make money. That kind of makes sense. It's a little bit correlated, maybe. Another great one was, I think, rating was good, was interesting. This was a good one. What do you guys think of this one?
It's a weaker correlation.
Yeah.
So just because something is critically acclaimed or critically panned does not correlate strongly with whether or not it will create lots of views.
Yeah, so just because a movie's good doesn't mean it'll make money.
But also, it's like, the other thing to keep in mind is it's an average rating, right? It's a mean of all the ratings.
Right.
Like, a movie that has a 7.6 with 1,000 ratings is probably a stronger indicator of quality than a movie that has a rating of 8 with 4 reviews, right?
Yeah, yeah, absolutely. And then there are some where you need to take other things into account, like when like the reboot of Ghostbusters, I find like I just have to like be like, okay, 50% of these people are angry people whose opinion is not actually based on the quality of the movie. Awesome. And did anyone look at any other features that you want to share? It looks like some people were doing some extra things. Did anyone do anything cool?
Other than get errors, no.
That's fair. That's fair.
Did you
Yeah.
get any cool errors, though?
I got a cool one that just printed out all kinds of ratings, and it's all handy together, so I can't convert it.
What did you find?
I did a word vector with the description, so like pulling out like violence or like comedy.
Yeah.
Might help as like potential features on the line.
Yeah, absolutely. Absolutely. I think there was,
Could you repeat that, please?
oh yes. So what he did is he looked at word vectors, like things like violence and comedy, to see if like maybe violent movies do better, or more comedy, something like that. Anything else anyone wants to share here? Yes.
I looked at whether or not the number of letters in the title correlates to how much money it makes.
How did that go?
It made a triangle out of
Amazing.
Also, I found some fun like yearly spikes if you plot it by date or like month release.
Okay, cool. Awesome. Excellent. So,
I would also ask if anything surprised them about the scraping acting.
can ask what you want to ask them.
I was wondering, so during the break, there were a couple of things that folks mentioned, like, oh, I'm really surprised that this web scraping thing is so messy and haphazard. And I was wondering if there's anything that you were working on that kind of like, I didn't expect this at all, like, why are we doing it this way? If anybody had any comments or thoughts there. More of a like learning the tools question, less like movies are cool type of questions. Might be a little harder to answer.
I think just to echo what you said, how manual the process is, and I assume with a different site, you have to go through and do it all over again.
Yes, exactly. So
Web scraping's actually awful. I did have my PhD doing web scraping. It's like you can spend a lot of time just figuring out how to scrape the right data and get it in the right format.
and you know, developers make different decisions than other developers would make making the same website. And so no site is going to be the same. One reason we get so excited about the Wikipedia post with the nice little table that we put up is that's a gorgeous standardized table. When do you see that? Never. You don't. So those kind of things, you know, those 90 HTML tables, whenever you see those, you throw up both hands and, you know, it's like sing or something. Because most of the time you will be like clicking through and being like, okay, how can I be as specific as I can to get information? I'm wondering if there are any folks who have worked in web development who had any suggestions for doing that digging. Yes.
So one trick that I discovered a few months ago that's really nice is if you, like a lot of more modern pages now, their data tables are fed by an API call behind the scenes, right? So they'll fill the table in with an API call. If you can inspect it and find that API call, it's a lot easier to parse through that data because it's already highly structured than it is to go through and scrape the page.
How many people know what an API call is? We want to define real fast.
Okay, so essentially it does a JavaScript call to the server to get the data formatted as like a JavaScript object that it can parse through and add. So it's like a structured data request that your browser is making behind the scenes after the page is loaded, and it does it to fill in data in your HTML table using JavaScript.
And the big lesson here today is 1, API calls are wonderful. You should turn to them. They're highly structured and they'll make your life better. 2, you should find yourself a web developer as a friend and just like have that friend forever because
Or you can learn web development yourself and be your own friend.
look, we all make choices. But it is very helpful to step outside of however you use Python and see how other folks are using it as well. I see a couple
Okay,
more
yeah, I
hands.
see 2 more questions, then we also still have part 2.
Anyways, but is there, like, the sleep function, is there a way to put in a maximum number of requests per time? You know, like if a website says like you can only make 60 requests in a minute.
Yeah, I don't know it off the top of my head, but I would believe that it exists. I would probably look at time.sleep.
And Pandas can actually make the GET request for you, and it can actually parse the table for you too, put it right in the data frame.
Oh, that's very fabulous.
Could you repeat that?
Yeah. Apparently, these days, Pandas can make the GET request for you and put the data in the data frame for you. So you don't need to bother with Beautiful Soup.
Maybe that depends on the.
Yeah, I'm not convinced that that actually works in all cases, but I'm sure with structured data it works very beautifully. Yeah.
And I don't think that it would be using a fetch via JavaScript, for this is probably server rendered. But how would we do this if it was, say, a client-side rendered app, like a React app or Angular app or something? We wouldn't really be able to do that, right?
Yeah, you wouldn't be able to do something exactly like this. I think at that point you'd be stuck figuring out things like the API calls. Yeah, figuring out if they have some kind of public API. Awesome. So this is a great breaking point if anyone wants to take 5 minutes to take a 5-minute break, and then we will be ready for the next, starting part 2. Okay. So in the last section, what we did is the question we were asking is, we are movie producers. We want to make a movie that will make us an absurd amount of money. This time, we're asking a slightly different question. At this point, we don't care so much about the money. What we want is eternal fame and glory. We want to win an Oscar. So now we're optimizing not for money, but for awards. Which, on some level, you're predicting something a little bit different there, and that what you're trying to figure out is you're trying to figure out what people want, particularly the people judging the Oscars. And it turns out that there are actually some things that you can do if you want to make a movie that wins an Oscar. So to start off with, we will this time do just a short thing where once again, previously we talked about how to ask good questions, working with the data, exploring that. Something that we'll do different this time is we'll learn a couple different types of regression. And then we'll also talk about, after we've used regression to develop these models of how the data works, we'll talk about how to see if our models are any good by looking at different types of errors. So to start off with, we are going to try to ask another set of questions, which is given this new life outlook and data set that includes all the information we could want about every movie ever made, including those that had won Oscars previously, what kind of questions do we want to get out of this data? So if you can break up into your small groups, and we will spend 2 minutes doing this time. Yeah, that's a good one. If you have someone with, so the idea is what is the likelihood that they'll win an Oscar, that the movie will win an Oscar if you have an actor or actress who has already won an Oscar, which makes sense. Yeah, or if you just have Meryl Streep, then of course you're going to win an Oscar.
The idea of a vertical
Yeah.
We don't care what the actor wins. But if I build a crew, my actors, my screenwriters, my musical people, do I need more people that have had recent Oscars, or do I need a few people that have had a longevity of Oscars?
Oh, that's a great idea. I like that. Yeah.
Along with that, not just how many Oscars they've won, but Oscar nominations as well.
Okay, yeah, so that is, along with Oscars, how many Oscar nominations, which it sounds like another great idea.
Well, you can create like a score maybe out of how many you won and how many nominations and a ratio of that.
Yeah,
Be a better, I don't know.
yeah, that, I'm sorry, can you repeat that one more time?
That like, because they're like actors that have like so many nominations but only won one or two,
Mhm.
and then there are other ones that the ratio between nominations and wins is better.
Yeah.
So then maybe create like a separate variable out of those two numbers.
Yeah, that's reasonable. So she's saying some people, if they get nominated, they win. And other people, like poor Leonardo DiCaprio, has just been nominated for ages, and it took him ages to actually win. So, yes, how about you?
I was going to say not just Oscars, but other awards that they've won. So,
Yeah.
you know, some films will work really hard to make sure they get into certain film festivals or are in consideration for other awards. Those can often be predictors of.
Yeah, awesome. So his thought is to use, what about other awards, not just Oscars, but making sure that you get into certain film festivals or win awards in those film festivals. That seems like another great thing that could be predictive if we have that information. Anyone else want to share something? Yes.
Wondering if we could use revenue as or gross as a predictor of Oscar success, but control for things like the number of screens it was released on and things like that. So maybe profitability, something like that. So are more profitable movies likely to win Oscars or less likely to win Oscars? Like, is there maybe a negative correlation?
Yeah, that's another great thing to think about. So are more profitable movies more likely to win Oscars, or are they maybe less likely to win Oscars if you control for all the other factors?
And then the other thing was to maybe segment the Oscars, right? So
Mhm.
like there's the prestigious Oscars, right, which are the ones like Best Actor, Best Actress, Best Picture, Best Director. But then like the total number of Oscars include a lot of like technical accomplishments
Mhm.
that may not be our category of the Fame and Film Award, right?
Yeah, like best cinematography.
Right.
Yes. So there are some Oscars that are more prestigious than others, and we want to look at all those Oscars, you know, as something like best cinematography or some of these other things that are technical achievements rather than fame and eternal glory. So yes, that is an awesome idea. We can look at that as well.
One thing I've heard that have come out.
Speak up.
One thing that I've heard that have come out in a few of the examples is like there are plenty of things that you would need like some domain knowledge about. Like we can take some pretty good guesses, you know, when we're talking about, you know, maybe if we put in more money, we'd get more money. But as far as like what film festivals should we be looking at that we think kind of indicate eternal glory / Oscar wins? You know, that's something that we would need, there would have to be more research, you know, our data science brains are going to be looking for the data science pieces and not necessarily the Oscar pieces. So in our formulation of our questions, that's another thing to notice is when those come up.
Awesome. Oh, yes.
The other one is genre and rating too.
Yeah.
Maybe like if I want to guarantee getting an Oscar, it might be better to try to make an animated feature-length film because there's only 4 or 5 produced a year versus 20 or 30 that are contenders for, you know, like an R-rated drama or something.
Makes sense. Awesome. So, excellent. Those were some great questions. We'll be able to answer some of them, and some of them are great questions. However, we just had a late-breaking update, which is actually we do not have all of the data we could have for every possible movie. And it turns out that to get all of that information, it turns out to be a lot of movies, and there are some rate-limiting factors, and it's actually going to take weeks to get all of that data. So instead, what we have is we have a bunch of features, in a spreadsheet that could increase the likelihood that the movie will win an Academy Award from 1981 to 2005. And so what can we do with that? Is there any way we can salvage this situation? No? Everything is over. So what we can do instead is we can still find that we can say what is the problem. We can say that we have all this information about movies that have won. So instead we can try to correlate features of movies that have won with the movies that we're trying to predict for. But to start off with, we will need to do more exploratory data analysis to make sure that we understand our data. So to start off with, we can print the first few rows of our data frame. I think most of you, as I recall, most of you have used data frames. Do you remember how to do that? Head, yep. So you can print out the first few rows of the data frame. So what does this look like? What this looks like is it looks like a bunch of features, and some of these are binary data. So in this case, it's like if it's an action movie. So if it's a comedy, it's a 1, so it looks like this first movie is a comedy. The next one is a drama with crime. This is a fantasy comedy. So we have a bunch of these binary features. We also have features like what movies was it nominated for? So we have information about the nominations. So was it nominated for Best Actor, Best Actress, Best Animated Feature Film, Best Art Direction, Best Cinematography. So we have all these things, all of these movies that were nominated, and then we know whether or not they won. So what we can do is we can figure out if any of these features might be predictive or somehow correlated with winning. So there's a lot of different information here. There's also building on the person who was sitting there's idea. There's this about language. You can also say, you know, is this a blockbuster film? Did it have blood? Was there cigarette smoking in this? Were there family relationships in this? Flashbacks. Flashbacks are definitely going to win. Was there violence? Another one. And then was there a winner? And then was it a winner? And what year did it win in? So this is the information we have to work with. Excellent. So I will give you a few minutes to explore the data frame and tell me what you think. I think from looking at this, I think this will only take a couple minutes. Yes. This will only take a couple minutes. I'll give you 1 minute. And then we'll reconvene for the next stop. Excellent. So at this point, so we have all this data. We have information about, we've looked at the headers. We've looked at all the different type of information we have. And so now we want to do some exploratory data analysis here to answer a few questions. Some of which we could answer are like, do some countries tend to win more Oscars than others? Which is totally possible. What is the frequency of top keywords among Oscar winners? So this is like cigarette smoking, family relationships, violence. What genres tend to win Oscars? And in what month do Oscar-winning movies tend to be released? So to do this, we'll start by making this list of genres, countries, keywords in our data set. And this is a lot of stuff that took a lot to run, so instead we're just loading all of these for you here. So these are genre list, keywords list, a dictionary of countries. Then we create a dictionary of countries and how often countries win, and sort those countries by ratio. And then we are able to make this plot. So it looks like Italy wins a lot of Oscars. And these are all error bars here, so some are a little bit clearer than others. That's probably because Italy is making fewer movies than the USA. So we have very small error bars than the United States. So we have small error bars in the United States and larger ones on Italy and Spain. And USA, France, Germany, and other countries. And I was supposed to ask you what you learned from that plot. Did you learn anything other than what I said?
Well, this is only a ratio of nominated movies.
Yeah. So this is if you were nominated.
Like there you win.
Yeah. So it's if you were nominated, and then you won.
It really looks like a lot of the reviewers are from the United States. I don't know.
Yeah, it's possible. Okay. So next, we want to figure out what are the most powerful plot elements. Do epic war battles win Oscars? Do they need romance? What works? And you can follow a pattern pretty similar to what we did in the last example here. And actually, it looks like, is this the solutions? No, it looks like I accidentally gave you the solution here. So you can just run it and we can discuss it. So what do you guys think of this one? Yeah, I found this one. So if it's a blockbuster, that's likely to win. Or title spoken by character, I found that one kind of interesting.
Well, so I
Yeah.
was fiddling around with this, and I thought title spoken by character was interesting, so I was just like messing around with that number, and I looked at it, and only 17% of the movies that were nominated for Best Picture had their title spoken by a character in the movie. So I thought that was an interesting relationship to square off against that.
Yeah, that is really interesting. Apparently not many people know this. We should all go make a winning movie and make sure that we say the title as frequently as possible.
What does it mean in the context to be blockbuster movie? Like, are we talking about the old-fashioned blockbuster, like the one that you go and pick up?
A blockbuster is one that does really well in the box office.
Yeah, yeah.
Is there a clear definition?
Yeah, is there a clear definition for this? I don't remember. We do link to all the data sources though. As it turns out, Flashback did do great. Friendship and Murder are also great. Character name and title is a close second.
Apparently movies need really strong emotions.
They need strong emotions, blood, singing, and cigarette smoking. Families work.
The weird that father-son relationship is a bit above mother-son.
That could actually just be a factor of the fact that there are more men and women, more male characters than female characters. So there's more data there.
I'm assuming the son that you throw is like kid.
Yeah, yeah, maybe. Yeah.
Right, it could be there too, maybe. It's always
Okay.
yeah, but I'm curious.
So this next one is going to be interesting. You can follow a similar pattern as the first two, and you can answer the question, which genres are most common among Oscar-winning movies? So does an Oscar-winning movie need drama, romance, crime, comedy? And so we can use a similar analysis as the last two. So notably, what you'll want here is you'll still want the keywords and the genre information to sort the movie and calculate the standard error and store it in X error. So you can sort of follow along with what's happening in these last two and see if you can replicate it. This is a little bit longer. Let's do, I'll check in 10 minutes. How many people have a plot? Awesome. And if you don't have a plot, that's also okay. Because you can always check your solution against the solutions in the other notebook. And we can continue on. So this is what it looks like. It looks like news is a big thing in Oscar-winning movies, but it also is, I guess, what are your impressions of this plot? Does anyone have any thoughts they want to? What was that? I'm sorry, I didn't hear you.
Abraham Lincoln.
Yes, Abraham Lincoln gets Oscars. That's true. Does anyone else have anything that they thought when they saw this?
I think the margin of error on news is extremely high.
Yeah. What do you think might be going on there?
There's not enough observations.
Yeah, probably. What should the plot of our Oscar-winning movie be?
Historical biography. Or lose a war and lots of music.
Yes. Probably. Right.
And the tale is spoken by the characters, so that matches well with the biography.
Awesome. So, in here, so we're trying to figure out the relative importance of the genre, and it seems like what we need a movie, an historical drama biography, where the name of the character is the same as what's in the title. So there's a couple other questions we can answer, one of which is, when are Oscar-winning movies most often released? And so to start off with, what do we need to do there? We want to figure out how many Oscar-nominated films are released each month, and then look at the winners. So we do some of this for you here. And let me make sure that I have an action. Excellent. So now we have the raw number of nominated films by month. What do you think? So it seems like a lot of movies are released around December, which kind of makes sense. Everyone wants to go to the movies. It's cold. You have to find something to do with your family that doesn't result in you all killing each other. Yeah, Maria.
When do Oscar nominations begin?
February.
Yeah, so then December is pretty close to that.
Yeah, so it's also like good recency effect.
Yeah. That's why because January, a good portion of them might not have seen it yet, whereas December still has that time chunk where they were able to see it if there's a vacation kind of built into it for many people.
Makes sense. What do you think?
I think this possibly gets into the issue you were talking about at the very beginning related to causality and correlation, which is that I think that it's known that by releasing the movie later in the year, close to when they're going to be reviewed, it's more likely to be top of mind. So movies that where the goal is to make them an Oscar contender are often released during these times. So I don't think we can tell whether releasing the movie late actually makes it a better Oscar movie. I think it's just that Oscar movies, people that want movies to be nominated for Oscars, release them at this time.
Right.
We don't know which way the arrow goes. It's just they're rated.
Right. Yeah, that's a great point. Is there a way that we could start getting at that?
That's a good question.
What was the point if I was far away from this person?
Oh. So what was your name?
Dan?
Dan made a great point here, which is that it's hard to tell anything about whether there's which way the arrow is pointing on the causation here. All we know is that it seems like a lot of people are releasing movies in December, but that could be because they are trying, but that could just be because the people start reviewing them in February, and so they know, everyone knows that December is a good time to release the films, so they release the films then just because they want to be considered, not because their films are amazing. Awesome. So this shows us all the raw number of nominated films by month. But the next question that we can ask is, these are the nominated films, but given that a film is nominated, how many winners do we get per month? Like, are there actually more winners coming from December, or is everyone just releasing their films then? So that's the next step. The code's going to look pretty similar to this, except you'll want to normalize, instead of just looking at the raw numbers per month, you'll want to normalize by the number of winners, so you can actually lift that idea from up here, where we were checking if there was a winner, meaning it was equal to 1. Awesome, I will give you another 10 minutes. So how many people have the raw number of winners by month? Awesome. Maybe we can take a moment to look at that. So remember, previously we saw that there were a lot of nominated films in December. It looks like there are also a lot of winners in December. And there are also a lot of numbers at the end of the year. And there are also a lot of winners around the end of the year. So what do you think is going to happen to the ratio? Yeah. Yeah, it might actually end up being a little bit flatter. Has anyone gotten the ratio yet?
The top 5 are pretty close.
Yeah, so it actually ends up being relatively flat, kind of as we expected. But it does still look like the end of the year is good. July is also good, though. I mean, you basically just don't want to put it out early in the year. So that's pretty cool. That's a pretty cool finding.
When you say flat, what do you mean by that?
I mean, these numbers are all close to each other in the ratio. Whereas it looked like this number is really big, but if you divide a big number by a big number, it gets much smaller. And the ratio is actually pretty similar to how many movies, given a movie comes out at a certain time and is nominated, and then wins. It looks like it's sort of, you can put it out in any month between August onward.
Yeah.
And it has a similar probability of winning. So do you guys want to spend a little bit more time on this or move on to regression? Okay, actually, let me phrase that differently. If you want to move on to regression, raise your hand. Okay, cool. Let's do that. Awesome. So the point of all this was sort of to get a sense of what was going on in our data and making sure that we understand what all these ratios are doing and getting a sense of some of the ways that we can manipulate the data to get more information out of it to answer our questions. And now what we're going to do is we are going to use regression to try to develop something more of a predictive model, if you will. But this is actually still just correlational. So in this case, so we'll talk about a couple different kinds of regression. If you look at this, as you can tell, you can get a lot of different information out of a regression. In this case, this is the same bunch of dots, but you can either say, oh, it's not correlated at all, or you can say overfit and draw like a very fancy Rex Thor, the dog bearer, and have it fit great. So you want your line, you want your model to fit the data, but not to fit it too well. Because if it fits it too well, then you've overfit to the data, and if it sees more data, it's not going to be accurate. It's only going to be accurate for that training data. And then there are a couple of different kinds of regressions we'll use. One is linear regression. So in linear regression, the outcome is continuous. It looks something like this. You would usually use some sort of error minimization like ordinary and least squares. In a logistic regression, this is a good example. So these are two different data sets. And a linear regression is going to look like a line fitting these two. Whereas a logistic regression curve, the outcome is going to be either a 0 or 1 probability. So there's this curve, which then defines if you're on one side of the curve, it's going to be very high. If you're on the other side, it's going to be very low. So logistic regression has a binary outcome. Linear regression tends to have a continuous outcome. And then when you're using regression like this is something we sort of started to think about in the last section, but less so. Then you need to think about underfitting versus overfitting. And just like the XKCD article, you can see, like this is an example of underfitting. It looks nothing like it. This is overfitting where it doesn't, where it sort of has fit too much, so it has very high bias, low variance. And then this is an example of something that basically fits the line. So we're going for something in the middle, something that's a good fit. So to prevent this underfitting and overfitting, what we can do is we can add a penalty term to keep our regression from taking any one data point too seriously. So it's not going to overfit to the data specifically. And that penalty is called a regularization. And the two ways that we're doing it here are Lasso and ridge regression. And the way you think about these are, in Lasso regression, it uses a loss function, and the loss function uses a squared error. And in ridge regression, the loss function is the absolute value of the error. This blog post does a good job of describing it. Oh, except apparently it's not, it doesn't have a, apparently its SSL certificates are down. But anyways, the difference here is that it has a, is just the term that it uses. Does it use the squared value? The Lasso method uses this difference of squares as the term, and the other one uses the absolute value. So the Lasso uses the absolute value, and this one uses a squared error term. And they're just different ways of making sure that it doesn't take that for each data point, rather than fitting exactly to that data point, it's fitting just a little bit off of the data point. So when you're developing a model, you want to make sure that you fit the model. And the way you fit them, I guess how many of you are familiar with like making sure that how you split test data and training data? Okay, so you want to make sure that you train with some data, and that you also, and then that you test with some other separate set of data, so that is different, so that you are able to evaluate how well it works. So here what we do is we do some pre-processing, so we split this data into training data and test data. So we take some, will be some of these values that we're going to test on and others that we don't. This, given how we are in time, I might skip over this a little bit, but what this does is this goes into the details of specifically how this library does the classification in order to and grid search in order to make sure that it classifies these. So here we do grid search, and we figure out which of these estimators are best, and we get some accuracy. And it looks like I have not run this. So I will run this. Yes. So the important thing here, I'll figure out what's going on with the running, but I'd say to start off with, so what we do here is that we run this regression where we classify for a logistic regression, and we get some accuracy and we get some training. But here, what we're doing here is we're using a confusion matrix. And who remembers what a confusion matrix does? Okay, so the idea of a confusion matrix is that it says, it allows you to look at what types of errors your system makes. And this is actually, ends up being a very big deal that often gets forgotten in a lot of machine learning projects. Often it's easy to say, oh, I have a model, it fits the model, it has 80% accuracy, that's great, or better yet, it has 95% accuracy. But actually, if you don't look at the pattern of the errors, often you can end up with a system that is biased, where it is systematically selecting one thing rather than another. So in this case, we might say, want to say if, given that some movie has been nominated, is it, so because all of our data has been nominated, given that a movie has been nominated, is it, and does it actually end up winning the Oscar? Does our system predict that if our system predicts that it won't win an Oscar, but it actually does win an Oscar, then that means our predicted condition is negative, but the condition is actually positive, so that's a false negative or a type 2 error. Or we could also say that we think that it is going to win an Oscar, but then it doesn't win an Oscar, so that's a false positive. So putting this into our example, the true positive is great, that means we got it right. The true negative is also great. That means we predicted it wouldn't win. Our model was right. But we should look at our false positives and our false negatives to understand how this is going. So a baseline example here is we say, what if we just say, actually most movies don't win Oscars. Even if it's nominated, most movies don't win Oscars. So if we just predict that everyone is a loser, our model actually does pretty well. Has almost 72% accuracy. So you can see how this could expand out to all sorts of other things too. If you're like, my research during my PhD was in medical data. So if you're predicting the occurrence of a disease like a cancer, and you could actually get an extremely accurate model by just saying no one has, if you're looking at a rare cancer, just say no one has cancer, and you might be up to like 98% accuracy there. So it's important to look at not just your accuracy, but also exactly what that pattern of errors is. And then similarly, if we say that the baselines are all winners, then we have a 30% accuracy, but we can see that it's biased in the other direction. And this is a specific formula for getting the accuracy specifically. And recall, precision and recall. So what some people will do is they'll put together the F1 metric is a combination of precision and recall that where we can test how, on some level, how effective our model is. So then down here, do we actually have, yes, we have more stuff for you to do down here, I think. So then what we do is you can explore your errors, and there are a lot of reasons why you might want to check these, why you might want to check this information. So for example, an example of this is like movie makers are notorious for overrepresenting some parts of society more than others. So while like a movie audience is made of 50% women, only 20% of movie leads are women. So that means that if you're predicting anything about anything related to gender, there's a good chance that you'll, if there are fewer women in the movies, you're going to have much less data in that area, and it's likely to be biased. An example, a sort of like very direct example of this, have any of you heard of Joy Buolamwini's works at the MIT Media Lab? She was she's been in the press a lot recently, but she was an MIT Media Lab graduate student, and she was working with a lot of out-of-the-box facial recognition software from things like Microsoft, Amazon, a lot of these other big software chains, and she was trying to figure out, and she was just using the software as a library for her project, but she could never test her code because it would never recognize her face because she has dark skin. And the reason it would never recognize her face is because if you look at where the photos were coming from, the majority of them were coming just scraping online. At which point, if you look at whose faces are online most often, they're like actors, which are mostly white men. It's like politicians, which are even more white men. And so we ended up with, and so despite the fact that people were going through all of this, they found that when they looked at the overall model and how well that facial recognition software worked, it looked like it worked really well. They had like 97, 98% accuracy. But then what Joy did with her research is she split it up and said, okay, if we say someone has she divided things up by skin tone and gender. And she found that particularly it was worse for dark-skinned women. And it also was not great for dark-skinned men. But a sort of a nice positive tale here. So she found that, so first of all, she found that, so I guess to continue with her starting story, so she was working on this facial recognition. She couldn't test her own software. She found that it did a better job of recognizing this as her face. So if she put on a funky white opera mask that doesn't look anything like a face, suddenly it recognized her and said, oh, that's a face. And the reason is because you had all of this light skin data. So she ended up researching instead facial detection software, and she found that, and she published these results. And actually, a number of the facial detection softwares did actually go out and get more data for the areas that they were underperforming in. And so that the facial detection software is even more accurate. So that's an exciting way in which research had an effect, but also sort of like a very grave warning in the ways that you can think that you have software that works and it really doesn't if you don't take time to look at different segments of your data. Do you have any questions on that before we move on to checking out errors? Cool. So then another way that you can look at this, so we started out with these, with the confusion matrix, where we're looking at our pattern of errors. That's sort of like a great way to just start, is say, let's segment out our data in a given direction and look at that, and then let's segment out our data in another way. Like maybe let's, you can segment things out by like what region you're in, what zip code you come from, things like this. And then what the receiver operating characteristic does is it actually lets you compare those two types of errors and see what types of errors you, and so it lets you plot your true positive rate against your false positive rate. So you're looking at your accuracy against your positively predicted errors. So when you're looking at a receiver so it's just another way of looking at the data from that confusion matrix. And usually what you want is you want there to be as much area under the curve as possible. So you want a high true positive rate, and you want a low false positive rate. So I believe I'm looking at the solutions right now. So we got the RC curve, awesome. And now we are actually at the end. Do you have any questions? If not, I can leave you to those last plots.
Might also be a good time,
If you have something to say, you might want to come up to the mic.
Oh, I was just going to say it might also be a good time to let them know what will be staying online and what will be coming down.
Yes, that is a great idea. Okay, so a few things to note. One is we would love to hear how this went and what was confusing so that we can make this better. There's a feedback form here if you have time to fill it out. And also, we are going to be taking these servers will be coming offline, but everything is still going to be up on GitHub. D. Hanus, Oscar. Oscar's tutorial, yes, was there, and then Oscar 2's tutorial. So this is up on the internet. It has all of the information here. We have the two notebooks that we went through, and we also have the solutions and all of the data here. So you are welcome to fork, clone, and you can do all this on your own machine as well.
So if you go home and you're thinking thoughts about the workshop and like what was good and bad, we'd love to hear about it on the survey.
If you're speaking, you should speak here.
Anyway, so there's the survey link on the end there if you have thoughts about the workshop itself. If you go home and you're fiddling and you have a question or something, and if you use Twitter, on each of these little sheets we gave out, there's a hashtag here, and we'll be watching that. So if you want to send us a tweet or say something hopefully nice because it's Twitter, but so if anything comes up, that's also a good way. If 2 months from now you're tinkering around and you're oh shoot, what's going on, or this doesn't work or something, that would be.
Also, our names are all on the repository as well.
Yeah.
We are, yes. You figured it out.
I used to tell. Go ahead.
Awesome. So I guess if there are no questions, we will let you go. And if not, we will be around here for the next, for the next several days, actually. And you should feel free to reach out.